Hey everyone, in this video we're going to talk about rolling contact bearings and specifically looking at bearing types and load life. This is the first video on rolling contact bearings, and this is part of a lecture series on mechanical design 2. So rolling contact bearings is our module 3 in our class, and what we're going to be doing here is we're going to be covering a few different topics. So I'm going to go over the topics that we're going to cover really quickly. So topics covered. We're going to cover the bearing types, and we'll look at bearing types today, but we'll look at that more in depth as well. Bearing life, and we're going to look at load life, which we have in our title here, at rated reliability. And finally, we're going to look at bearing survival, and we're going to go into more depth on bearing survival. So this is all going to be part of this module three lectures, and all of this rolling contact bearings chapter that we're going to go over here. So before we get started, what we want to look at is kind of think of what are bearings and what they actually mean and how we use bearings. And this is sometimes something that engineers don't really know when they start studying bearings from a starting point. So before we get started with understanding what a bearing is, let's try and think of a primitive form of bearing. So if you think of bearings, you think of something rotating, and a typical example where you would have bearings nowadays that is an everyday item, or at least for kids would be, for example, a skateboard, right? We know that a skateboard has bearings in its wheels, and typically what it does is it connects a fixed shaft, which would be fixed to the skateboard, and a rotating wheel. Okay, you have the same types of bearings on cars in order to connect essentially a axle of the car with a rotating wheel, for example. Okay, so thinking of that and thinking about that, what is an idea for a primitive form of bearing? So there's many different ways in which bearings came about, but one of the first ways in which humans used bearings was they actually used them um, back in when they would do construction. What they would do is they would line up logs on the floor, so wooden logs in width, and what they would do is instead of carrying a piece of construction material or a stone or something like that, they would roll it on logs. So they would have this material here and they would move it along and they would roll it along logs. So these logs would roll out and eventually would step out of the way, and then you would move the log back to the front of the line, and you could move stuff for a lot less power than you needed to in order to move stuff. And the advantage of bearings over moving something, for example, let's say we didn't have a bearing and we just had the same material moving on the surface. Well, one way would be to carry it, the other way would be to slide it. So here you would have a sliding motion. And the main advantage of a bearing is you essentially get rid of that sliding motion, which has a lot of friction. Okay, and so what we can write as a summary is that the main load in bearings is transferred in what we call rolling contact. And we can say that this is done rather than sliding. And this helps us a lot because the friction essentially goes down a lot as well. Okay, and we can say that there are 4 essential elements to the bearing that we need to know about. So there are 4 essential elements to an actual bearing. Now, the primitive bearings was just a log, but if we look at a modern day bearing, then we would know that it would have an inner ring, and we'll show a diagram of an actual bearing in a second, but it has an inner ring, it has an outer ring. So I'll over exaggerate the width of the outer ring just so that we have some space. Okay, so it has an outer ring. This inner ring and outer ring can have a certain thickness. Right now they're just shown as non-thick materials, but they could have a thickness. And then in the middle, what we're going to have is we're going to have these separators, or these essentially cylinders, or what we call, it could be a ball, it could be a cylinder, it could be a roller or a needle. These are rolling elements. And what these rolling elements do is they allow the inner ring and the outer ring to roll on each other. So the inner ring and the outer ring would roll, so we could fix one and rotate the other one, or fix the other one and rotate the opposite. So you could have inner fixed, outer rotating, or outer fixed and inner rotating. Now, the other thing we need to add to here is some sort of separator. And what the separator does is it keeps the rolling elements in place, and it also separates the inner ring and outer ring, so the inner ring and outer ring don't crash into each other. Okay, so those are the four main elements of our system. And what we're going to do now is we're going to look at some examples of these bearings and look at what they actually look like based on diagrams. So first things first, first diagram shows a bearing with, we can see the outer ring as well as the inner ring. So we have the inner ring here, the outer ring here shown. We have the shoulders, which are the edges of the outer ring. We have an inner ring ball race, so that would be the spacing for the ball to fit inside the inner ring. Same with the outer ring, there's a ball race. And then you see all the, in this case, it's a ball bearing, okay? So you can see that there's a bunch of different balls put into our bearing all around. And they're held by a separator or a retainer. So you can see the separator there to hold the ball in place, and also make sure that there's a separator between the inner and outer ring. And from there, we basically come up with a design. Now, there's many different types of ball bearings, and we can show all these different types in figure 11 too. So you can see there's deep groove, filling notch, angular contact. There's a bunch of different designs here that are drawn in sort of a schematic way, but you can also look up these different bearings by looking up on an image search, which could give you an actual visual of what the bearings look like. Now, the problem is that bearings are kind of enclosed, so you don't really see the inside unless you cut it open. So here you have some cross sections of what these bearings look like. And we're going to be using all different types. So we're going to be using deep groove, angular contact. Essentially, they all work in the same way. The only difference is the tables for each one are going to be slightly different. So you would use, for angular contact, you would use a certain type of table, and for deep groove, you would use another type of table. But we're going to try and keep that analysis pretty simple, but if you want to go into more depth, you definitely can on that side. The last is different types of roller bearings. So instead of having some ball bearings, what you can also do is you can have a roller bearing instead, with some rollers as opposed to having some, or essentially cylinders instead of having a ball bearing. So you could have a straight roller, spherical roller, tapered roller. There's many different types, needle bearing, steep angle tapered roller, and you can see all these different rollers. But essentially, what the difference between the two is, one would have a ball to rotate around, which allows more rotation in all directions, essentially, and creates maybe slightly more friction. The other is a roller bearing, which is a little bit more precise, essentially. But those are the main two differences. So the next thing we want to talk about, now that we've kind of seen what these bearing looks like, is bearing life. So we want to talk about bearing life and what we mean by bearing life. And for this first video, we're really going over definitions to make sure that we have all the definitions in place, so that then we can start analyzing these systems into a mathematical framework. Okay, so bearing life. So bearing life is defined in um, in two different ways, okay? And the first way is, of course, bearing life could be affected by two different things. It could be affected by metal fatigue, because usually we have metal bearings, okay? They're usually made out of metal because it can be machined very precisely, and therefore we use that material. And the other way in which it can fail is if there is a problem with assembly or design or other. Okay, so if there is a general problem. Now, what we're going to focus on is bearing life assuming that we have only metal fatigue. So we're going to always assume that the operation of our bearing and everything that we do with our bearing is done in a way that is the most optimal, and therefore we won't have any other types of problems. Two different types of problems that we could have, so I'll just work from there. So we're going to assume that we're going to look at the bearing life for a bearing that is clean and properly lubricated. And then the second thing is we're going to assume that it is sealed against dirt and dust. And therefore, metal fatigue will be the only mode of failure. So we can say that in green here, metal fatigue will be the only mode of failure. Okay, so based on this, we now have a definition for what our bearing life would be, and we know that bearing life is defined by just metal fatigue. Now, there's two ways in which we can measure bearing life. Okay, so two ways to measure, and the two different ways in which we can measure is, number one, we're going to look at the number of revolutions, and I'll put number of revs, of the inner ring with the outer ring stationary. So here we assume that we have an inner ring rotating, the outer ring is stationary, and we count the number of revolutions. Now, the problem with this is that we could have, we don't really know at what speed the revolutions are happening, but we'll talk about that later as we go. Now, number two is, instead of counting the number of revolutions, we can count the number of hours, or the number of hours, equivalent hours of use at a given standard angular velocity, so essentially at a constant RPM, until tangible evidence of fatigue. So what we mean is, essentially, in order to measure so I'll add here bearing life in brackets. In order to measure the actual operational life of a bearing, we can state it in two different ways, and we're going to run the bearing until it basically fails, okay? Or you can see tangible evidence of fatigue. And one way to measure it is to say, okay, we're going to do an experiment. We're going to have the outer ring stationary, the inner ring is going to be moving, and we're going to count the number of revolutions. The other way is to say we're going to use the number of hours at a standard angular velocity until we see some fatigue. And based on those two different methodologies, we can then come up with a graph of what happens when the bearing fails. And then we can define a life based on that failure graph. So the ABMA Association, so it's the American Bearing Manufacturers Association, so not AGMA, but ABMA with a B, defines what bearing life means. So we can say that ABMA, what it does is it looks at doing one of these two experiments, okay? It's going to look at bearing life bearing failure versus the life of the bearing, okay, or bearing life. And what the bearing life is going to look like is the following. So we're going to have some sort of graph that's going to look like a bell curve. Okay, so we're going to have a bell curve to show our bearing failures. So that means that essentially a lot of our bearings are going to fail at the same life. Some bearings are going to have fatigue very early. There's a few examples. So if you run the experiment for, let's say we run 1,000 experiments, some bearings are going to last until here, some bearings are going to last until here, some bearings are going to last until here. And so you have this kind of graph that adds up in terms of where the failures happen the most. So we can see that the failures that happen the most are at this bearing life. Now, in order to satisfy the bearing life, typically what we do is we say that the bearing life is defined by 90% of its 90% of the bearings would not fail, and that would be the minimum life of the bearings. So if we take that into account, we can say that up until around here, we have 10% of the bearings would fail before this point. So before this point, 10% of the bearings would fail. So in this area, we have 10%, and in this area, we have 90% of the bearings. So what we can say is that the bearing life will be this amount of hours. So for example, this point could be 10,000 hours. So we can say that our life of our bearing is going to be equal to, so the life of our bearing is going to be equal to 10,000 hours based on a reliability of 90%. Okay, so what we're essentially saying is that we know that around 90% of the bearings are going to last 10,000 hours in this case. Okay, and this is just an example. Okay, it's not a real thing, but it's just an example to illustrate what's happening. So based on that, we can then talk about how we talk about rating life. So the rating life of a bearing is calculated in the number of revs, as we talked about above, the number of revs or hours, depending on the way that we measure, or hours at constant speed. Okay, so we have, that's going to be called our rating life, which we just defined above in the graph. We can say that 90% of a group of bearings will achieve this life. And this is also called the minimum life. Okay, so there's many different ways in which this rating life is called. So we can call this rating life the minimum life, where it means that this is the minimum life of our bearing. It shows that the bearings have at least 90% of efficiency. It's also called L sub 10. It's also called B sub 10 sometimes, so depending on the notation. And it's also called L sub R, for L sub R being the life rated or rating life. So typically, what we do is we define a arbitrary reference point for all bearings. So we say the rating life of a bearing is going to be LR is equal to 10 to the 6 revolutions. And so we're going to measure how effective a bearing is at 10 to the 6 revolutions, okay? So bear with me while we talk about this. It'll make sense once we get a little bit further into the video or in the future videos as well. So we can say that typically, and as an arbitrary point, the ABMA association says that the rating life of a bearing can be defined as L sub R is equal to 10 to the 6 revolutions. Okay, and this is, I'll write it in my notes so that you have it, but this is an arbitrary reference point. And based on this arbitrary reference point, we can now start looking at how this will be used later on. Okay, so we're going to skip to something else now, and then we'll get back to this arbitrary reference point in a little bit, and hopefully it'll all make sense once we get there. Okay, so what we're going to do is we're going to talk about typical load life for bearings. So what typical load life means, and what it essentially is trying to determine, is based on the amount of force on a bearing, we might have a different life for the bearing as well. So in addition to just rating the life at 10 to the 6 revolutions and thinking of the life of a bearing based on its revolution, we also need to look at life based on the amount of load that we put on the bearing. So typically, if we were to draw a diagram with force versus life of the bearing, we would have something that looks like this. Okay, and let's say we could do different experiments at different forces. So let's say we did so we would test a bunch of the same bearing at different forces. We would get a curve that looks something like this. And the data points would probably be somewhere like this, and we would do a curve fit of the data points. Okay, it looks like a curve that increases towards the left, and this is obviously not linear, so we're going to add that it's not linear. And clearly, if we try to analyze this, it means that the more force we put on the bearing, so force goes up, means that life goes down, and that makes sense. Okay, the life should be shorter if the force is higher. Okay, then the next thing we can do is we can say, well, because this force and life are somehow correlated, we can try and curve fit the graph. So we can try and figure out an equation. Now, in order to figure out an equation for a curve of this shape, so for a curve of this shape, what we can do is we can take the log of f and the log of life, and we actually end up with a straight relationship between the logarithmic functions, essentially. And the only thing we need to figure out is the power that we need to figure out to get the straight relationship between log f and log life. So what we can do is we can redraw the graph that we have above in terms of log f versus log life. And then we have our data points are now going to be somewhat in a straight line. And if we draw a straight line through it, we would get a straight line relationship, which makes our equations a lot easier to solve. So then what we can say is, thanks to this graph above, we can say that f times L to the power of 1 over a, and this is just notation, but it could be to the power of a or to the power of something else, is equal to a constant. So this comes from the fact that log of f is equal to some value of log of life or some multiple of log of life. And if we use the logarithmic rules, we get that FL to the 1 over a is equal to a constant. So it's always going to be constant because it's essentially we're finding the slope of the line. So this is where a is going to be equal to a certain value. And this is true for most bearings. And so a is going to be equal to 3 for ball bearings. So for ball bearings, we can use a is equal to 3, and we would get the relation that we usually see for ball bearings. And then a is equal to 10 over 3, so slightly higher than 3 for roller bearings. Okay, so moving forward from this, then we can say that we can now combine the forces with our reliability. Okay, so let's say we want, for a reliability of 0.9 or 90% reliability, okay, so if we remember, reliability means that 90% of the bearings won't fail at that certain life. We can say R is equal to 0.9, so we'll call reliability R. We can say that if F times L to the 1 over A is equal to a constant, then we can also write that that means that since F of L to the 1 over A is equal to a constant, we can start solving for different reliabilities if we wanted to. Okay, so we could start solving for different reliabilities or different forces if we wanted to. And what we can write is we can say that F sub R LR to the 1 over A, and I'll talk about that, what that means in a second, is equal to FD times LD to the power of 1 over A. Okay, and we have R is our rated, okay, and D is our desired. So let me talk about that for a second. So, for example, we know that we want to do experiments on a certain type of bearing. Now, instead of trying to test at many different forces and many different lives, what we can do is we can say, well, let's test all of our bearings at the rated life of 10 to the 6. Okay, so we know that this is 10 to the 6 revs. If we test at 10 to the 6 revs, we can figure out when we have 90% reliability, so when we have 90% reliability, we can test for different forces and we can figure out a force rated. So we can say, for example, the force rated will be 22 pound force. Okay, just making it up. Okay, so we look at a reliability of 0.9, we go to our graph here, we test at different forces, and once we get to the number of revolutions that is correct, and we get 90% reliability for that, then we know that that's the force equivalent to that. So we can say that the force is 22 pound force. Now, let's say that our life desired is not 10 to the 6 revolutions, it's actually 10 to the 7. So I want to find 10 to the 7 revs. So what I can do is, because FL to the 1 over A is constant, then I can find F of D, or my force desired for the system. So the force desired will probably be something that is less than 22 pound force, okay, based on the equation. And you can find your F desired based on this, okay? So obviously, based on this equation, we can say that, and it'll make sense when we start doing examples. Maybe it doesn't make complete sense here, but once we start doing examples, it'll make complete sense, okay? So what we can say is, as desired life goes up, our force has to go down, okay? Just based on the equation. And L, in this case, is going to be in units of revolutions, okay? So the amount of revolutions. And what we can say is that revolutions can be converted, so the L can be converted in time, in minutes, multiplied by RPM. Okay, so if we multiply time in minutes by RPM, we get the total revolutions. And then we can go one step further, and we can say that L is also equal to 60 minutes over 1 hour. So a conversion between 60 minutes and 1 hour. And that would be multiplied by the life in hours. So I'll leave it like this so that we know that it's a unit, multiplied by N in RPM. Okay, so if we have the life of our bearing in hours at a constant RPM, we can convert it to revolutions if we want to. Or vice versa. If we have the life in revolutions and we want to convert it to life in hours at a certain RPM, we can do so by this equation. So this equation is just a conversion between our life in revolutions versus our life in hours. So we can simplify this equations to L is equal to 60 times cursive L times N. And this cursive L is going to be always our life in hours. Okay, so we're just going to convert our life from basically our hours to our revolutions if we want to through the cursive notation. So going further than this, what we can say is that FR can also be written as, so F sub R can also be written as F sub R times 60 times LR N sub R to the power of 1 over A is going to be equal to F desired times 60 times life desired but in hours times ND all to the power of 1 over A. Okay, so just converting the equation back to the other side. And this FR can be found from a catalog, usually. And it's usually called the catalog rating. And this catalog rating is in pound force or kilonewtons. So it's the rating that we put in a catalog for a number of revolutions that is standard. And that number of revolutions is 10 to the 6 revolutions. Okay? And this would yield to us, so the catalog rating is sometimes also called C10. Okay? Because it's called C10 because our catalogs test for 10 to the 6 revolutions at 0.9 reliability. Okay, so anytime you see a catalog for bearings that is standardized, you would have a test being done at 10 to the 6 revolutions for a reliability of 0.9. And then so far we've learned that we can modify or figure out our force desired if we are looking for a different life. So we're looking for our force desired if we have a different life assigned to our bearing. So let's say we want to run, instead of 10 to the 6 revolutions, we want to run 10 to the 7 revolutions, then we can find our FD based on that and our force desired, and then we will go back and pick the right force based on our catalog rating. Okay, but we'll get into that once we start doing some examples problems. It'll be a lot easier to solve for. Okay, so What we do to find the catalog rating, just to simplify, we've already talked about it, but we would run 10 to the 6 revs and find our force at failure rate of 10%. Hopefully this makes sense. Okay, then we can simplify. We can rearrange that above equation either with life in revolutions or life in hours. Typically, we like to use revolutions because it's easier. It's just one term. It's not 60 times LR. It's just L. Okay, and we can rearrange to find our force rated. So we can say that our force rated is equal to the force desired times life desired over life rated to the power of 1 over A. So we can find our catalog value based on the force desired and L desired. So typically what we do is we say, okay, we have a force desired, we have a life desired and a force desired of this much because we know our application. So let's figure out what we need in terms of our force rated in our catalog. So we typically need a higher force rated than the force desired if we're going to have a longer life in our system. And this is equal to C10. So then we can go and look for our values in a catalog. The other term that we're going to include as well is that X sub D, or it's a new term that defines the rating life ratio. And this term is really not necessary. It's just an extra shortcut. Instead of writing LD over LR every time, we can write XD. So XD is actually equal to LD over LR. And in most cases, except given otherwise, we would write this as LD over 10 to the 6 because we know it's 10 to the 6 revolutions. Okay, so let's assume that we have, let's do a quick example to try and apply these equations and try and understand what we're trying to do here. Okay, so let's try and figure out, based on a certain desire that we have and a goal reliability that we have of 0.9. So for now, we only know about reliability 0.9. We don't know how to change reliability yet. But let's solve a problem and try and find a force desired. We know that a bearing is going to withstand a certain force due to the fact that it is going to be used in an application where we know the exact force is going to be applied to the bearing. So let's do an example and try and figure out what bearing we would use in a catalog, or what value of catalog bearing we should use. So we have a goal reliability of 0.9, and we're told we have to use a ball bearing. And this ball bearing is going to have a life of 25,000 hours as a goal, and it's going to rotate at 350 RPM because the machine that we're using is rotating at 350 RPM, for example, that we're applying this bearing to. And we're told that our force desired should be 2.5 kilonewtons. Okay, so we have to use 2.5 kilonewtons, and we have to use it for 25,000 hours. So let me add here that this is life desired and this is N desired. So now my question is, the question that I'm asked as an engineer is, what bearing could I possibly use, or could I use? Okay, and in order to figure out the bearing that I could use, I need to go to a bearing catalog. And we'll look at tables of bearing catalogs in future videos. Here, I just want to find the value of my bearing catalog that I would have to go find. So in my bearing catalog, I know that I have values for C10, or in other words, I have values for my FR or F rated. So I'm going to need to find what bearing I can use. So the first thing I would do is write the equation down. So I would say, well, I need to find C10, therefore I can find C10 through the fact that C10 is equal to FR, which is equal to FD times XD over to the power of 1 over A. Okay, and we know XD is just LD over LR. So let's calculate what LD over LR is first, and then we can go from there. So we would say that XD is equal to LD over LR. I know that my life rated is 10 to the 6 revolutions. Now, my LD is not given in revolutions. It's given in hours and revolutions. So what we're going to do is we're going to use the conversion between the two. We're going to use 60 times 25,000 hours multiplied by 350 RPM, which will convert it to a value of revolutions. And we get that the value of XD is 525. So that means that I want my bearing to last 525 more times than the rated reliability. Okay? And that means that essentially, since I want it to last 525 more times than its rating at 10 to the 6, it means that I need a bearing that will last 10 to the 6 revolutions. I need a bearing that will withstand a much higher force probably. Okay, since it's only tested for 10 to the 6 and not 525 times 10 to the 6. So if we then plug that into our equation, we get that our C10 is going to be equal to 2.5 times 525 to the power of 1/3. So 1 over A is 1 over 3. And that would be equal to 20.17 kilonewtons. So that means that I would then have to go to a catalog and essentially find a bearing that has a rating that can withstand 20.17 kilonewtons as opposed to 2.5 kilonewtons, just because of the fact that I increase the life by 525 times. Okay, and one way I can show you this on an actual graph and try and show you the representation of what's happening is to look at the graph of log of F versus log of life. Okay, and you could do this with a graph of F versus life, which wouldn't have a straight line, but we know that log of F versus log of life for a certain bearing is given as a straight line. And we can say that our desired value at a reliability, so we're going to call this line at a reliability of 0.9. So this line is for a reliability of 0.9. We'll look into that later because it's important for later. We can say that our first operating point, and I'll draw it in black just so it differs from the color. So our first point is going to be what we have as our L sub D and what we have as our force desired. And we know that our force desired is 2.5. We know our L sub D is a certain value. Now, obviously, this graph is not to scale at all. Okay, I'm just illustrating what's happening. But what we know is that since this graph represents the equation above, well, we know that in order to figure out what type of force I need to figure it out at my L sub R. And I know that my L sub R is equal to 10 to the 6. Okay. I know that L sub B is 525 times 10 to the 6. So we know that this graph is probably not very aligned, although it is a logarithmic scale. So it does kind of make sense in terms of the logarithmic scale. Then I know that my new operating point would be here. So I would have my L sub R would cross the line here, and so I know that my force rated will have to be higher. And based on this graph, which is a visual representation of the equation above, we can find that F sub R is equal to 20.17 kilonewtons. Okay, so we can use the equation or the graph. The graph is just a visual representation of the equation. Okay, so we're going to end this video here. And in the next video, we're going to talk about how reliability works and how we can come up with a way to solve for a reliability that's other than 90%. So how do we modify our system to define a reliability that is either greater than 90% or lower than 90% in some cases. So we'll see you in the next video.